Hi, everyone. My name is Ricardo Calaon, and I'm a PhD student at the University of Colorado Boulder in Dr. Hans-Peter Schaub's ADS laboratory. And today I'm going to be talking to you about constrained attitude maneuvering using modified Rodrigues parameters-based motion planning algorithms. So with constrained attitude maneuvering, we're talking about the problem of reorienting a spacecraft that has also positional constraints, and such constraints can consist in a sensitive payload that must avoid bright objects such as the sun and the moon. And these are classified as keep-out constraints. We can also have keep-in constraints represented by some payload that must be kept within a certain angular distance from the direction of a celestial object. Think, for example, as sun sensors that must not lose sight of the sun. So the solution that I'm going to be providing to this problem is based on the idea of sampling the attitude space with a three-dimensional grid in MRP space. The strength of using MRPs for this implementation is that a unit sphere centered in the origin is enough to represent the entire set of attitudes that can be assumed by the spacecraft without loss of generality. So this is done with a grid of equally spaced nodes where we define n as the number of nodes along each semi-axis. And the equally spaced nodes are complemented by extra nodes added on the sigma equal to 1 boundary to map those points that represent attitudes that are 180 degrees away from the origin. We need to define a metric d hat in this attitude representation, which is the minimum between the Cartesian distance between two MRP sets and the Cartesian distance between one MRP set and the shadow set of the other one. And this is done to account for shadow set mapping, which is a property of MRP representation. So here on the left, we can see two shortest paths between two sets of initial and final conditions, sigma A and sigma B. And both these paths are minimum distance path with respect to the metric that we just defined. Specifically, the green path is a path that remains within the unit sphere, whereas the purple path exits the unit sphere and re-enters from the opposite side. And this is possible because the two nodes on the boundary have a mutual distance of 0, because being the shadow set of one another, they represent the same attitude. Therefore, they have 0 mutual distance. On the right, you can see a central node, a generic node, where with central node, I'm talking about any node that is far enough from the sigma equal to 1 boundary that it will be surrounded by 26 neighbors. So you can see the central node in purple and the 26 neighbors in red, in orange, and yellow. So at this point, we have basically constructed a graph consisting of nodes and edges. And what we need now is a graph search algorithm that can perform the path planning query from an initial attitude to a desired final attitude. This is done with the A-star algorithm, which is both optimal and efficient. It is optimal in the sense that it can find the path that is optimal with respect to a cost function that we can define, but it is also efficient in the sense that it minimizes the number of nodes that it needs to visit before finding such optimal path. This is done thanks to a heuristic function, which is an estimate of the cost to go from node n, which we're currently exploring, to the goal. And for A-star to work properly, such heuristic must be optimistic, which means that the cost that it's estimated, it must be smaller or equal to the cost in the path that we're gonna compute eventually. So before we actually move to the path planning query, it is interesting to show how these obstacles, keep-in or keep-out obstacle cones, map into MRP space. Here on the left, we can see the spacecraft principal body axes, X, Y, and Z. And the x-axis is highlighted in red as it represents the direction of the sensitive payload, with 3 obstacles in red, green, and yellow. And on the right, we can see how these obstacle cones are mapped into MRP space. They almost always are mapped into structures, tubular structures that extend from one side of the unit sphere to the other side of the unit sphere. And their thickness depends on the half-cone angle of the obstacle cones. In these cases, all the obstacle cones have a half-cone angle of 20 degrees. Here, we're showing the exact same thing, only with 2 obstacles that do not quite match this description because The yellow cone is located at a 0 angular distance from the bore site, whereas the blue cone is located at a 180 degrees angular distance from the bore site. So we can see that the yellow obstacle on the right takes a shape that encompasses the whole sigma 1 direction, as any rotation about the x-axis is going to remain constrained in compliant. Whereas the blue cone is mapped onto this ring-shaped blue obstacle that is located at the intersection between the sigma 2 and sigma 3 plane with the unit sphere. So this is a first metric-based A-star solution, which is, again, based on the metric, it tries to minimize the cumulative distance between between all the waypoints in our path. And what we can see is that this solution is indeed constraint compliant. However, this solution is nothing but a sequence of attitude waypoints connected by a straight line from one another. So what we want to know now is, how do we navigate between these waypoints? What we need, therefore, is to convert the sequence of waypoints into a trajectory that is sufficiently smooth and differentiable, and also should match the desired angular rates at the endpoints, specifically at the beginning and at the end of the trajectory. This is done using B-spline interpolating functions, and these are piecewise polynomial functions of a desired order P. For this implementation, an order P equal to 4 is sufficient to provide first and second order derivatives that are also smooth piecewise polynomial. And these B-splines manage to exactly interpolate n+1 waypoints. The strength of using B-spline interpolating function as opposed to regular polynomial interpolating functions is that being piecewise polynomial, they don't wiggle between the waypoints as the number of waypoints grows. And to compute the B-spline function that we desire, we need to solve a linear system of n+3 variables, which are called control points Pi. And n+1 equations are provided by the condition of exactly interpolating the n+1 waypoints. And the two additional equations are obtained by enforcing the endpoint derivatives, specifically the initial and final angular rates for our maneuver. So this is a visual representation of what we obtain if we interpolate the metric-based A-star solution that we previously showed. And as we can see, we went from a piecewise linear, very edgy path to this smoothly interpolated path. And here we can see the interpolated attitude as a function of time. It takes about 150 seconds to perform the maneuver. And together with that, we show angular rates, acceleration, and torques, where the torques are calculated based on the mass properties of a 3-unit CubeSat. What is interesting specifically about the angular rates is that we're able to match endpoint requirements. Specifically, we're trying to perform a rest-to-rest maneuver, so initial and final angular rates are 0. And however, we see that during most of the trajectory, the angular rate magnitude does not remain constant. This is something that is usually desirable when performing a slew maneuver in space. So it is actually possible to track the same trajectory while maintaining a constant angular rate throughout the maneuver. I'm not going to get into the details of how this is done because it's very cumbersome, but here I'm showing the results. So the trajectory that we're interpolating in MRP space is basically the same, but it's taking 140 seconds to track it instead of 150. Whereas if you look at the angular rate profile, we can see that the magnitude is constant throughout most of the maneuver. It's equal to 0.03 radians per second. And it features a ramp up and ramp down portions at close to the endpoints to match the endpoint derivatives. And this is the kind of implementation that you're going to be seeing in all the results that I'm going to be showing in the next few slides. So what we want to do now is to update our definition of the cost for the A-star algorithm, because what we're really interested in finding is not the path with the smallest travel distance, but the path that has the smallest required control effort. And this is done by defining the cost of a path B as the integral of the control vector, of the magnitude of the control vector over the entire trajectory. And for a path that is currently exploring node sigma n, the heuristic is defined as the integral of the control magnitude vector over the portion of the trajectory that goes from node sigma n to the goal attitude node. This basically consists in assuming that the trajectory can go from the current node to the goal without having to steer the spacecraft around to avoid any other obstacle, thus ensuring a minimum amount of torque required to perform the maneuver. And this is where the optimism of the A-star relies on in this implementation. So this is the same test scenario that we have been analyzing so far, only in this case, the solution is computed using the effort-based A-star graph search. And we can see that the computed trajectory is very different from the previous one. Specifically, we see that we're steering to avoid the yellow obstacle in the beginning, and then we're putting onto this coasting arc that is almost like a straight line, of which we can understand more if we look at the plots in the next slide. Specifically, if we look at the torque plots, we can see that we're applying a relatively higher torque in the beginning and in the end to steer the spacecraft from the initial attitude and to the final attitude. But during about 50% of the maneuver, the torque required is virtually zero, which means that for about 50% of the maneuver, this trajectory is cost-free. We're not requiring any torque to be performed to track that trajectory. So that's exactly what we wanted. And we can see from the angular rate plots that we're still performing a rest-to-rest maneuver with a constant angular rate magnitude in between. This other case is interesting because if we remove the blue obstacle from the scenario that we saw so far, we can free a path that is basically an eigenaxis rotation about the body z-axis, which is also interesting because in the MRP space, this path is exploiting MRP shadow set mapping, thus exiting the unit sphere and bouncing back from the opposite side. And if we look at the plots, we can see this very nice bang-bang profile where we only apply torques around one axis in the beginning and the end of the trajectory, while during most of the trajectory, the spacecraft is free coasting at a constant angular rate of 0.03 radians per second. Another interesting case is obtained when we try to perform a non-rest to rest maneuver. Specifically here, we have an initial angular rate of 0.03 radians per second along the Z body axis. And what the algorithm does in this case is that it tries to follow the initial angular rate of the spacecraft as long as it can. So we can see that it follows that direction until it needs to steer the spacecraft away to avoid the blue obstacle. And this is validated by looking at the plots. Specifically, the angular rates remain roughly constant for the first 20 seconds, and the required torque remain very close to zero, also for the first 20 seconds of the maneuver. This last example is one that features both keep-in constraint and keep-out constraints, and specifically, we have two sun sensors located on the Y and Z body axes of the spacecraft. And these sun sensors only need to be constraint compliant one at a time. We don't need to have them both be able to see the sun at all times. So we can see from the bore side paths that the sensitive instrument in red is still constraint compliant because it's avoiding the red keep out constraint. And the two sun sensors are also constraint compliant because at all times, at least one of them is able to see the sun because it is within the green keep in constraint. Specifically, sun sensor number 1 is constraint compliant in the beginning, and sun sensor number 2 is constraint compliant in the end. And these are just the regular plots for a rest-to-rest maneuver. So in conclusion, we were able to provide a solution to the constraint attitude maneuvering problem. Such solution is obtained by interpolating a set of waypoints using B-spline curves, which are smooth and differentiable with smooth derivatives. And we're also able to match endpoint requirements on angular rates in the initial and final parts of our maneuver. These solutions are optimal with respect to the control effort L and of course, with respect to the discretization level that we're using. Future work will address the influence of the discretization level N as a tuning parameter for the optimality of the solution, as well as different strategies to sample the workspace in comparison to the three-dimensional grid that we're using. If you have any questions, feel free to reach out to me. Here's how to do that. And thank you so much for your attention. And I wish you a very pleasant rest of your day.